attention to this thing for a little while, it doesn't like it. Does that sound familiar? And I'm trying to get my of course. So, okay, so we'll just run the movie again. And okay, so same thing. Ordinary weighing, balance weights against other weights, and then hope for electromagnetic weighing. Okay, so do the same thing, balance the weight against an electromagnetic force, and now here comes the new and beautiful part. We take that coil that had current in it, that was creating the force, and now what we do is we open the coil up and take the leads out to a voltmeter and move the coil in the magnetic field of the permanent magnets. And every time it moves, it creates a voltage. This is what a generator does, right? It turns out that knowing that voltage gives you all the information you need about how strong the magnetic field is and where all the wires are. Then you can do the other part where you put current in the coil and you measure the force and you're done. Now I'll show you the details of how that works in just a moment. You've now got two different parts of the experiment. One where you weigh and one where you measure voltage. So the voltage, so when we do the weighing, we have a mass, we have the acceleration of gravity, that turns it into a force. You multiply that by the velocity of the coil from the other experiment. Okay? Now, force times velocity is power, right? On the other side of the equation, we have the current from the weighing mode, and we have the voltage from the velocity mode. Current times voltage is power. This is mechanical power, this is electrical power. If you've got a good system of units, those two things have to be the same. That's why we call it a watt balance, because we're measuring mechanical power in watts against electrical power in watts. And so, well, that's just what that says. Okay, so we combine these two parts of the experiment in the same apparatus and solve for m, and we find that that mass is equal to the current in the weighing mode times the voltage in the velocity mode divided by the acceleration of gravity and the velocity in the velocity mode. Now, that's how it's done. But wait a minute, I promised you that this was going to relate to Planck's constant, right? And I haven't told you anything about Planck's constant yet. But Planck's constant comes in because the modern way of measuring current and voltage is quantum. We measure current and voltage, actually we measure voltage and resistance, but if you can measure resistance and voltage, you can measure current. Today we measure voltage and resistance in a quantum way. And those quantum ways are called the quantum Hall effect, due to Klaus von Klitzing, and the Josephson effect, due to Brian Josephson. Now, I'm not going to give you a lecture on the quantum Hall effect and the Josephson effect, even though those are incredibly beautiful physical phenomena. We just don't have time. I'm supposed to be finishing in a few minutes. So, instead, I'm just going to tell you that when we measure voltage, it's related to a set of fundamental constants, Planck's constant divided by twice the charge on the electron. Twice the charge of the electron because it's a superconducting system, and in a superconductor the electrons pair up, and so we've got 2e. So h over 2e gives us a unit of voltage, and current is proportional to the charge on the electron, and using the quantum Hall effect, we get a quantum value for resistance, which when combined with the voltage for the Josephson effect, you see you put a certain current through a resistor, it creates a voltage. You know the resistance in terms of the quantum Hall effect, which is E squared over h, and you know the voltage in terms of, well, the resistance is h over e squared. You know the voltage in terms of h over 2e, and when you put it all together, what you're left with is E. And that E cancels out this E, and you just got H. So that's the magic. I know that was a little bit quick, but believe me, it's true. So, So what you have is the mass is proportional to Planck's constant. So when you define Planck's constant, you have a new definition of mass. Here is a picture of a modern watt balance at NIST. And with this watt balance, with this kibble balance, the kilogram can be realized to a part in 10 to the 8th. What I didn't mention, I should have pointed out, the drifts of the kilogram are several parts in 10 to the 8th. So that means we never know what a kilogram is to several parts in 10 to the 8th. This fixes that. This makes it absolutely stable at a part in 10 to the 8th. Here's a group of people at NIST who've made the final measurements 40 years after I first started to work on this, and believe me, these people are serious metrologists. You remember that in ancient Egypt, that it was punishable by death if you didn't calibrate your these people have tattooed the value of Planck's constant onto their arms. They are serious about metrology. So, how many of you are serious about your studies to that degree? Now, it turns out that when you define Planck's constant, you haven't told people how they must realize the kilogram, how they must get a kilogram from that definition. I've shown you one way, the watt balance. It turns out there are other ways. I alluded to the fact that we could weigh photons, but that isn't good enough yet. But there's another way that involves making a perfect sphere of silicon. Why does that work? Well, it turns out that if you define Planck's constant and you measure the Rydberg constant really well, and you've defined the charge on the electron, which we've also done, then the thing that's uncertain in the Rydberg constant is the mass of the electron. So what it means is, when you define all those things, you know what the mass of the electron is in kilograms. You can then compare the mass of the electron to the mass of the proton in kilograms, okay? And then you compare the mass of the proton to the mass of other things, like carbon. And then you compare carbon to silicon. Why silicon? Because of the semiconductor industry, we can make perfect crystals of silicon. You make a perfect crystal of silicon, measure the lattice constant, and measure how big the thing is, and now you know how many silicon atoms there are in it, and you know the mass of the silicon atom because of this long chain from the Rydberg constant. And it turns out that's just about as good as the kilobalance. It gives you a kilogram to a part in 10 to the 8th. So some people are doing it that way, some people are doing it with the kilobalance. All over the world, there are metrology laboratories that are doing it by one way or the other. When they all agreed to within a few parts in 10 to the 8th, then it was time to make the redefinition. And so the rest of the story, very quickly, is that there is a new definition of the ampere. So I've already told you about the old definition of the ampere, the one that I'm sure you've all memorized. Now, the new definition of the ampere is that the charge on the electron is defined to be a certain number of coulombs. And since an ampere is always a coulomb per second, that means that an ampere simply becomes a certain number of electrons per second. Now, with both E and H defined, it means the Josephson constant, 2E over H, and the von Klitzing constant, the quantum Hall constant, H over E squared, are both exact. And that allows us to make electrical measurements in absolute units using the von Klitzing effect and the Josephson effect. Now, little known, even to physicists, is the fact that up until May, we had two different sets of electrical units. We had the one you all know, the International System of Units, in which the ampere was defined in terms of forces, and that was all you needed. And the other constants were defined in such a way as to make electrical power equal to mechanical power. However, as I've mentioned, it's really hard to use that definition of the ampere to measure an ampere. And so what people were doing instead was measuring the voltage across a resistor using the Josephson effect, and the resistance of that resistor using the quantum Hall effect, and that gave them all their electrical standards. But those were not the International System of Units. It was just a set of convenient standards that was really easy to do to high accuracy. And ever since 1990, the entire world agreed on fixed, chosen values of 2e over h and h over e squared, which were not the SI values. They were as close as possible to what we knew to be the SI values, but they were not SI. And as we did better and better, we realized that these were deviated from the true SI values. And on the 20th of May, that all changed, because we now had SI defined values for 2e over h and h over e squared. And so finally, we have a unified set of electrical units where the SI and the practical legal set of electrical units are the same. And this is just to illustrate how we can do that. Now, finally, as you heard in the introduction, we've changed the definition of the mole and of the Kelvin. So formerly, as I'm sure you all remember, the mole was the amount of substance that has a number of entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. Not true anymore. Now, we've simply defined Avogadro's number. Much simpler. The Kelvin used to be 1 over 273.16, the triple point of water. Well, that was clear enough. It's not that easy to measure where the triple point of water is. And so now, it's done by defining Boltzmann's constant. The Kelvin is just defined as being that temperature that leads to the energy, the thermal energy being equal to whatever it is when you use the Boltzmann constant. Thermal energy of kT, that's in joules, which is a mechanical unit, and that defines the new definition of temperature. So, the French Revolution brought us the metric system, with length in meters and mass in kilograms. The Convention de Mètre in 1875 made the entire international community agree on a single system of units, what we now call the International System of Units. And on May 20th, which is the anniversary of the signing of the Convention de Mètre, that's why it's World Metrology Day, the international community made this revolutionary change in which 4 of the units of the SI were defined in terms of fundamental constants. And so this marvelous picture of liberty leading the people means that we're going to be free of artifact measurements. The kilogram is the last artifact, and we're free of that last artifact, and we'll be free of a double standard for electrical measurements because we have a single standard. And so we have all the base units of the international system defined by fixing constants of nature. And so what that means is that you can carry the International System of Units in your wallet. Here's the list of all the defining constants. And so you might say that we finally achieved the dream of the French revolutionaries for all times, for all people. And I was in Versailles, where the International Conference on Weights and Measures met in order to formally ratify this change in the International System of Units in November of last year. And I gave the last talk before the vote. And it was a talk sort of like this one. And then we had a vote, and 60 countries that were full signatories to the Convention of the Meter, much expanded over the original 17. 60 countries voted unanimously to adopt this new formulation of the International System of Units. So from Mexico to the United States to China to Russia, everyone agreed. When was the last time everyone in the world could agree on something? It was really, for me, a tremendously emotional moment. And this, I'm just going to show you 1 minute of a video. If my, I don't know why I can't ever get the, okay, we'll just, okay. So this is a little video that they made. Is the sound on? I hope so.